Yes. Do you want me to come to you?
Yes, only because I can't remember. Okay, so. Yes. Stop your circle. Yeah. That's a work in progress.
Okay. Like take your computer home today.
Well, I can take it home and plug it in.
Oh, that's just a battery?
And it's like just every time. Like my battery, it's fully charged, but I can't, like if I unplug it, my computer turns off.
Oh, yeah.
5%. So I, yeah, I'm working on figuring out how to I know, honestly. Yeah, this is
All right. This is like a really fast lecture, so let's get started. And you'll have a bunch of time to work on the workshop. So this afternoon, we're going to be making the game of life, which looks like this. So it's an animation, basically. It's a zero-player game, which is basically an animation. Which means that how this evolves is based on a set of rules, and it's always completely determined given a particular starting point. So this kind of simulation was developed by, this particular one was developed by John Conway, and it was kind of rooted in this philosophical quest for something like life, something that could be self-reproducing and exhibit complex emergent behavior without having all the gooiness of life. We're basically like trying to simulate the fact that even though we sort of think, or scientifically we kind of think that the fundaments of life are simple chemical reactions, what seems to actually happen is that life is capable of having extremely complex behaviors, including making dumb stuff like this. And it turns out that in fact you can do very complex things with the game of life. In fact, you can do everything a computer can do. People have built computers inside of the game of life, and in fact have built self-replicating machines inside of the game of life, and so on. So we find out that very simple rules can lead to very complex behavior, which does kind of give us confidence that the much more complex rules of quantum particle interactions can give rise to things like squids and people walking around. So the rules of life are simple. Life is played on a 2D grid of cells that are either on or off. So they are either dead or they are alive. Every step, the grid updates according to the rules all at once. And this is kind of important. You don't update cell by cell, because if you update a cell and it dies, that actually affects its neighbor possibly, right? What instead is going to happen is you check to see if a cell, you check to see what the next state of every cell will be, and then the entire world takes over, and every cell takes on that new state simultaneously. A cell that is currently alive will, in the next moment, be dead if it has fewer than 2 living neighbors or more than 3. So there's this nice balance where only with 2 or 3 living neighbors will a living cell continue to be alive. A dead cell will come to life if it has exactly 3 neighbors. That is, basically those 3 neighbors somehow reproduce and produce a cell there, and otherwise it remains dead. And so this is why, these rules are why it is important that we update everything at once. Otherwise, the game does not take on the emergent characteristics that it has with these rules. These are not the only rules for a cellular automata. People have come up with lots and lots of others. There's, in fact, a little notational scheme for how to express them, and a lot of them have very interesting emergent behavior.
What's the difference between underpopulation and overcrowding? Because doesn't both of those cause them to die?
Yeah, it's not different in terms of the effect. It's just the argument for why that rule
What
should be
makes
there.
them die?
Yeah, it's like the cell was too lonely or the cell was too crowded. As a mathematical exercise, no, it doesn't matter. They're just arbitrary rules. As an explanation of why it, kind of vaguely looks like life doing life's thing, that is a sort of weak explanation of it.
So I have a question.
Yeah.
What constitutes neighbors?
Good question. So the neighbors of the cell are all of the cells around the cell that touch it. Yeah, including diagonals, not including the cell itself. So a cell has 8 neighbors. This is, so we can actually watch, the evolution of the simplest stable life pattern. Maybe not the simplest stable, the simplest moving stable life pattern is called a glider. And it evolves like this. So we have, okay, so here are the number of living neighbors of each of these cells. This is going a little too fast, and unfortunately I can't stop it. And so we can kind of see that, like, okay, this one's going to die because it has 1, this one's going to die because it has 1, this one comes to life. Those 2 die, this out of overpopulation, this from starvation, and then we're back to the beginning. So this pattern actually walks across the grid in this kind of diagonal direction and serves as the basis for a lot of other more complex structures that people make inside of life. The other thing that's cool is that if you just create a big life board and spray random stuff on it, you'll see these things spontaneously emerge, of course. Especially because like a glider will emerge and it'll fly across and it'll run into something else which creates some complex pattern. And even like quite complex structures can emerge spontaneously. There isn't really a energy gradient or a fitness function in the way that like living, evolving creatures have. And so you don't really see a tendency towards more complexity, but it's still interesting to see that complexity emerge from essentially random initial states and very, very simple rules. All right. Any questions?
The black cell is the dead cell.
What's that?
The black cell is the dead cell.
Black cells are alive in
Okay,
this.
that's the one.
And so, oops. And so, like, this one dies, but then this one, which is dead, comes to life because it had these 3 neighbors.
Can you repeat how you would populate it in order for them to create a pattern? Like, where's the first alive cell comes from?
Yeah, so the workshop talks about this. There will be a couple of ways in the program you make to do it. One is just the user can be able to click on cells to toggle them from dead to alive, so you can draw a pattern and run it. The other is that there will be a button to just generate a random pattern. And those are both features that you will get to implement. There are test specs in this, so you'll be guided through a lot of the nitty-gritty of how to implement the rules, and then you have a bit more freedom when implementing the front end to make it look and work how you want. All right. So this workshop is not, the text is not in LearnDot. Sorry about that, but the text is in the README of the Git repo. So just you can just read it on GitHub and continue to file help tickets as normal through LearnDot, but you just don't have to be on the workshop there, and that's fine. All right. Any last questions? That's all.
It's in Slack.
Oh yeah, I selected Paris. Did I select out Paris? I did.